Well, if you work in manufacturing in either a quality or operations role, perhaps you've been in a position where you know that variation exists in your processes, and that results in variation in your product. You know that you are responsible for leading a team to improve quality and productivity. You're not really sure to how to determine if the variation that you see in your process and ultimately in your product is called common cause or special cause variation. Now, your boss would be very happy if you could improve both product quality and simultaneously reduce cost, and you need some help to proceed. Well, I welcome you to the Practical Problem Solving Clinic. This module is called Understanding Variation to Solve Problems. So in this package, we do have three parts. In part one, we're going to be defining what a problem is, strategy for solving problems, then talking about attacking variability in terms of problem solving. In part two, we're going to be identifying the types and sources of variability. Part three, tips on using control charts, ultimately to break down and understand variation. And in section 6, a challenge of where do we go from here? There are 7 modules in our practical problem solving toolkit. Structured problem solving, that's the 8D method. A focus on the process. Describing and controlling variation, that's using statistical process control. Determining capability and implementing control. The one we're discussing now, understanding variation to solve problems. And then on to experimental techniques and ongoing control. Well, I am Mike Vella. I am recently retired after a career of 42 years in operations and quality, 30 years at an automotive OEM supplier of safety critical parts, and the last 12 years of my career in a food manufacturing business. My undergraduate is in aviation engineering technology from Western Michigan University, and that's in Kalamazoo. And my MBA in finance is from Wayne State University, and that's Detroit. I'm a senior member and fellow of the American Society for Quality and a certified quality and reliability engineer. This is just a bit of a summary of each of those modules. The 8D package will show you how to form and lead problem-solving teams, what tools can be used to define a problem, getting to root cause by examining cause and effect, how to know how to make a rational choice when the options aren't clear, and that's happened very often in finding root cause analysis and making corrective action, and then using the 8D method to solve problems with an unknown cause. The package on statistical process control has a section on how we define quality, what variation means, how to describe variation using frequency distributions and histograms, how to statistically control variation using average and range control charts, how to detect out of control conditions of variables data using control charts, and how to use fraction defective control charts to control attribute data. The module that we're going to be talking about in this package is understanding variation to solve problems, what the definition of a problem is, what strategies are available for problem solving, understanding the attack on variability, identifying sources of variability, and tips on using control charts. Ongoing control describes first, second, and third level controls, best practice gauging, and then source control. The package on experimental techniques will discuss planning experiments, variable screening, hypothesis testing, and simplified analysis of variance, or sometimes known as ANOVA. And the package on a focus on the process describes defining processes, process control, and process capability. Then we use business and complex processes as examples of what we call process, and why focus on the process results in something we call profound process knowledge, and at the same time, continual control, meeting customers' expectations. But first, let's talk about what the definition of a problem is. Well, since we're talking about finding solutions to problems, H.L. Mencken said, "For every complex question, there is a simple answer, and it's wrong." So what is a problem? Could be called a question raised for inquiry, consideration, or solution. Or perhaps it's a proposition in mathematics or physics, or an intricate, unsettled question. A source of perplexity, distress, or vexation, or a problem could be called a difficulty in understanding or accepting. For example, differences and intolerance of cultural or political differences result in unsolved problems and sometimes result in armed conflict. Or the community you live in or the company you work for has financial problems. I hope not. He or she may have lifestyles that contribute to chronic health problems. My mechanic fixed the problem with my car. I don't know. There are a few problems with your argument. Ice and snow are problems in the winter, sun and rain in the summer. We must find a way to solve this problem. He or she is bothered by family problems. We didn't have any problems getting here, but we may have problems getting back. You know, I have my own problems to deal with. Mosquitoes are problems in the summer. Alcohol and drugs are serious health problems. And is addressing the solution of global warming a political or a scientific problem? Well, now that we've seen how the word problem can be used in many different ways, Kepner-Trigo has a definition of a problem. And Kepner-Trigo, again, you'll see a little description of who Kepner-Trigo is on the bottom of the slide. Their definition is a problem occurs when the is deviates from the should be. So if you envision what the expectation is or what should be as that horizontal line and compare it to reality or what is over time, that difference is called a problem. So how do we determine what should be? Well, we often set performance targets as part of the annual business plan. That's a should be. We accept customer specification for what's expected in dimensions, performance, quality, delivery, and cost. When we accept that contract, we accept what should be. Our families certainly have needs, which in turn create certain expectations for shelter, clothing, food, and support. That's a should be. We set our own personal goals. That's a should be. Governments creates laws which become enforceable and must be followed. That's a should be. And they define penalties for deviation from lawful behavior. Our culture, religion, and family beliefs define on what we consider right versus wrong, normal versus non-normal. Those are kind of different descriptions of what should be. The final analysis, anytime the actual performance, and we're talking about in manufacturing now, actual performance deviates from expectation, then we have a problem. So this is section 2, after that bit of an introduction, strategies for solving problems. So many formal approaches for problem solving have been developed over the last 50 years. All the techniques employ some structured approach of using facts, and that facts in the form of data determine the potential cause of the problem and what to do next. And they all have some things in common. The basic essentials of all problem solving relate to a single truth, and that is, if you can't define it, you can't measure it. You can't measure it, you can't improve it. If you can't improve it, someone else will. In the final analysis, for us to solve problems, data matters, and you have to have data, you have to have good information. Improvement is a necessary part of business life. It's not an option. Businesses that fail to change simply fail. If your business is not improving, solving problems, it's going to have problems in the long run being a viable operation. In order to improve, we must quantify problems using facts and data to guide the process. But before we can quantify that problem, we must clearly define a problem. As we say in the 8D module, a problem well defined is 80% solved. So we have some different models of solving problems. The first one that we're going to introduce is I'll call the Schuhart-Deming PDCA model. So you see Dr. Deming on the top and Dr. Schuhart on the bottom. This are a bit of a description of both of them. Their basic model is the plan, do, check, act. Plan the change, carry it out, study the results, and adapt or abandon the change, modify it. So why it's called the Deming or Schuhart? Deming has been credited with PDCA, but he said that he learned it from Dr. Schuhart. So I don't know who really gets credit for it, but I present it as the Schuhart-Deming PDCA. So again, the plan, do, check, act model. Plan to do it, just don't do it. You have to have a discussion, understanding with all the people involved what to do. Use a team to make the plan. Make that plan realistic and worthwhile doing. There's got to be some point where you just stop talking and make the plan happen. Get into action. Have a plan to check the process and the results. Develop a plan to determine how your study results will be evaluated. Check the results at the plan against the planned results, and then act to adapt or abandon the change. And you may have to go through this several times until you get to the desired result. Well, beyond the Deming-Schuhart model, the PDCA model, comes the Duran breakthrough model. What's pictured on the right-hand side of the slide is the Duran's Quality Handbook coming from my library. If you don't have this book somewhere close to hand, you probably need to buy it. It's great advice, great reference material for quality and operations professionals. Anyway, Dr. Duran speaks about study, stabilize, conduct experiments, and use control charts. First, study the problem by setting up a statistical control chart. That is, collecting data, setting up the control chart properly, which we'll be talking about a bit later. Stabilize the process by identifying and eliminating special cause variation. So you're going to learn an awful lot about your process by just doing this step. And then conduct experiments to improve by identifying and eliminating unwanted sources of common cause variation. Later on, again, we're going to be talking about the difference between common cause variation and special cause variation. And then use control charts to maintain those process improvements. Next is what we'll call the Bajaria SPS, or statistical problem solving method. Again, this comes from Dr. Bajaria's book, Statistical Problem Solving, a team process for identifying and resolving problems, by Dr. Bajaria and Richard Koop. Dr. Bajaria, a personal hero of mine, met him in 1978. Dr. Bajaria speaks about selecting and defining the problem by using control charts to measure the product, back to a bit like the Duran method. Then he speaks about listing, prioritizing, and evaluate and optimizing those process variables which are potential causes of the problem. So we talked about a Pareto analysis and understanding which of those process variables are most impactful in the process, which make a difference in the product. And then, for control, implement one of several permanent solutions, such as procedural changes, mechanical changes, poke-yoke, that's mistake proofing, and others, to bring the process back to center and reduce variation. Next is the Motorola Six Sigma method. So you see the Motorola logo on the right. Motorola was very, very big in process improvement, and they introduced something called the Six Sigma method. There's a note on the bottom that more describes what the Motorola idea was all about. But they're really, really advanced using packages of statistical toolkits to solve the problems. Their process is to carefully define the problem. Sound familiar? Set up measurables and determine if the process is stable. Not too much different than the Duran and Bajaria method when they're talking about understanding the process and stabilize. Analyze the data and then form theories and test the theories to identify causes of variation. Back to the special cause, common cause variation idea. Make improvements, verify the corrective actions you've taken are effective, and then control critical process parameters to maintain the improvements you've gained. Again, I think you see a pattern here, not too much different from in the overall shape of the concept, not too much different than the PDCA model, and then incrementally different from the Duran-Bajaria model. No matter what, all of these methods have something in common. They're all structured, and they use a systematic approach to the improvement process. They all begin with careful definition of the problem and planning before you just strike out and start experimenting and turning knobs. They are all data-driven. They use facts, and they rely on a statistical approach to understand what the results are telling you. And most of them really use a team approach. So this package of problem-solving tools that we've talked about in the first or second slide is what we call practical problem solving. It's a structured approach to attacking variability in our processes, and it's intended to be used on any problem that couldn't be quantified and measured. Well, here you'll hear a lot about the elements of practical problem solving in this package and in other packages we're offering here. But overall, it's a structured approach, fact-based and data-driven, and uses the broad use of the 8D method. That is using the power of a team, defining the problem. I urge you to go to the Gemba. That's the workplace to investigate and take corrective actions. Use of problem-solving, structured problem-solving tools in defining the problem, something called the is not, 5 W's and the 2 H's, who, what, where, when, why, how, and how many. Use of fishbone charts, timelines. Describing the variation using statistical process control and other graphical analysis. Finding and verifying root cause. Validate what you think the root cause is by using statistical testing. Once that path is established, taking long-term permanent corrective action. Use of hypothesis testing and design experiments to find the optimum levels of your variables. And then once you've taken corrective action on this particular process, use a systematic approach with other similar processes and management practices. Next, attacking variability. Well, we're talking about attacking variability, and perhaps sometimes it's easier for us to see or describe variability in a form of a picture. On the left, you'll find something called a frequency distribution, which is a graphic presentation of the set of all various values that individual observations may have and the frequency of their occurrence in the sample or population. So just at a quick glance, you can see that the average of that frequency distribution is at about 74. And the range, or the difference between the largest value in the frequency distribution and the smallest, is the difference between about 80 and maybe about 70. Now, a histogram is a plot of a frequency distribution in the form of rectangles whose bases are equal to the cell interval and whose area are proportional to the frequency. So the larger the bar, the more the frequency. Well, defining variation is very, very important in terms of understanding what the best quality is. So you might think best quality is easily defined as, pass, fail, or maybe it's used for definitions as fitness for use, or just meeting customer specifications. But if you haven't seen this before, I'll introduce Taguchi's continuous quality loss function. And the Taguchi method speaks about quality as best quality being targeted at the middle, and you lose quality and lose value, and that loss of value is borne by your customers as you move away from the target. Now, Taguchi was using this quality loss function at the time when he was working with his Japanese customers, who by and large were producing parts well within the specification, but he wanted to urge them to improve. So he developed this quality loss function and said, yeah, you might be well within the specifications, but you can get better, because as you move away from the target, you put those losses on your customers. So ask yourself, as a consumer, what product quality do you want? Certainly, we want the best. We want the ones that are targeted right at nominal. The best quality is that quality, those product process characteristics that are measured, that are exactly right on target. And the question is, how do we produce those? Because those products, those processes producing those products will provide us manufacturing quality at the least possible cost. Let's talk about quality again, and in terms of variation. Quality is best defined as minimized variation around a targeted process stream. So when you take a look at those two frequency distributions, which one has the best quality? The one on the top or the one on the bottom? Well, it should take you about 2 seconds to realize that the frequency distribution on the top is narrower. It has the smallest range, the smallest standard deviation. I don't know what the range standard deviation is offhand, but you can see it's smaller, it's narrower than the bottom graph. So therefore, the top graph represents the best quality. Variation, therefore, is the enemy. That's the thing that we want to avoid. That's the thing we want to reduce, variability. So our practical problem solving, or PPS, can be viewed as an attack on variability. Once we measure or quantify our problems and reduce them to numbers, our task then is to reduce variability. So on the right-hand side, we'll call the devil there the face of the enemy. Once we've selected a problem, we can carefully define it. We can begin to measure it. The next step is to determine the 3 types of variability we're dealing with. So understanding more and describing and controlling variability is our objective. So variability comes in 3 basic forms. First, normal variation from the mean, and that's typically described in terms of variance or standard deviation. Second, instability of the mean or standard deviation. Both of them can be described and identified using the average and range chart. And number 3, mean being off target. Well, we'll be talking about the 3 forms of variability in the next section. There are many different statistical techniques that can be used to identify and attack variability. The simplest and most widely used technique is the standard average and range chart, which is shown on the right. Well, here's the end of our first of 3 sections about understanding variation to solve problems. Please proceed to part 2, and we'll pick it up when we get there. But before you go, you can review this list of references and credits. Thank you very much.